Hi, my name is Ansley Gavron, and this is my Lab 2 for Physics 2211. So basically, the purpose of this lab was to observe an object falling and how the velocity of the system changes with a non-zero force acting on the system. So Newton's second law states that the net interactions of the system is a change in momentum over the change in time, and it's also the addition of all of the forces acting on an object. So since gravity is greater than drag, then we see that there will be a net force in the downward direction. So the experiment was the system was a marker cap that I dropped from an initial position of 1 meter with an initial velocity of 0, and the surroundings is the Earth. So here's the elements of the lab. This is a quick video of the ball dropping. There it is. All right, so here's a preview of the results of the computational models used in GlowScript and the tracker video experimental results that I had in the gray line. So the main physics ideas in their formulas is Newton's second law, which I went over in the previous slides, and the gravity on Earth is negative mg only in the y direction, and that's a force. And then the gravity constant is 9.8 meters per second squared. So drag is the drag constant times instantaneous velocity squared. And then we have the velocity and position update formulas that we use in the code. So by observing the data, we can assume that these principles will hold up in the experiment. So this is a result from the trackers. So we see that it started from 1 meter, which I had the axes originally as 0. So then as it falls, here we have it ends at 0.6. So here's the code used in GlowScript. So we set up everything, and we have the ball's mass, and then the position starts at 1. And then over here we have that the force of the net force is just gravity. So yes, and we have that up here, g negative mg. There you go. And then we use the velocity update and formula update, and velocity and position update formulas in order to find the position. Okay, so these are the results of the computational model for only gravity, and we see that it just kind of falls. And so this is the code for the gravity and the drag, and so for that, for net forces, we add the force of drag, and then here's that is the force of drag that we found from the formulas. And then we also have the proportionality constant, which is the drag constant, which I roughly estimated from my data. So here's the results, and we can see that it goes a little bit further before hitting the ground because it's at 0.5 and it's still not all the way to 0. So this is all of the graphs together. And so in the gray, we have the experimental, and the orange, we have the experimental or the computational model with drag, and then the blue is the computational model without drag. So we see that with drag, it takes a little bit longer in order for the ball to hit the ground, which would be expected because the drag slows down the force of gravity. So what does it mean? So terminal velocity happens when the force of drag pointing up has exactly balanced force of gravity pointing down. So this never happens in our experimental data or the computational data because it means that the net force is 0 and the velocity will be constant, and therefore it will not be that because we've seen through our graphs that the only one that really comes close to that is the experimental one, where here it's the slope, which is the velocity, is getting closer to 0, but not exactly. So the what if, so it was what if we threw the ball or the marker cap down with a different initial velocity. So if you did that, then it would be different because instead of just using 0, 0, 0, it now has higher values for the y component. And so the terminal velocity would stay the same, but the object would have to decelerate, not accelerate, in order to meet that terminal velocity. So in conclusion, this lab shows the effects of gravity and drag on an object falling from rest. We see that drag does not have that much an effect on force, as the velocity is never 0 at any points in our graph. However, it does make a tiny difference in the time it takes for the ball to hit the ground, as shown in the differences from the graphs. And that also could just be because of what we found in this. My errors could have been from my drag constant, because it was just a rough estimate, so not sure if that was correct. And then also the axes changes